Hello and welcome to YMT215 Logic Circuits. We are still discussing Chapter 2, Number Systems, Operations and Codes. This is the third part. In this part we will discuss hexadecimal numbers, octal numbers, binary coded decimal or BCD. Let's go through the topics one by one. The hexadecimal, we explained about two numbering systems. The decimal system, the system that we use in our mathematics and daily life, composed of 10 digits from 0 to 9. Okay, we spoke about it in details and how we compose the numbers when we are running out of digits or decimal digits. In this case, we compose two-column number and so on. The same idea is applied to another numbering system. We call it hexadecimal. Hexadecimal means base to 16. Base to 16, that means we have 16 digits from 0 to 16, but 16 we don't say it's 16 from 10 to 16, we don't say them 10, 11, 12. Rather we replace them by alphabet. So we have alphabetic characters that replace the two-column values from 10 to 15, not 16 actually. 16 is the base, we don't reach 16. I said 16 earlier, I mistakenly said it. We go from 0 to 15, but when we reach to 10, we don't say 1, 0, rather we say A. And then 11 we say B, 12 C, D, E, F. F represents 15, we don't reach the base is 16. Okay, so this is the idea. Exactly, we replace the two-column numbers in the 16 base or the hexadecimal system by alphabet. Why do we need to even have such a system? Well, we have decimal system, we use it in our daily life. We have the binary system, the digital system used for machine. Why do we care about hexadecimal? Hexadecimal actually is extremely practical, especially with big numbers, addresses of memories. We usually represent the addresses of memory in hexadecimal. Why? They can represent a large size of binary systems by single or maybe double or triple digits, sometimes more than that, but one digit from hexadecimal system is composed of 4 digits from binary. What does it mean? It means in hexadecimal system, each and every digit of the numbering system of the hexadecimal is represented by 4 digits from the binary. So imagine for 4 digits, that means a big number in binary. If we place 2 4 digits, that's a byte. 4 digits, that is 2 bytes and etc. So we can go to big addresses in hexadecimal in an easier way. Replacing 4 bits by just one digit is easier for us to deal with, especially human beings. Now look at this. So we have the decimal system 0, 1, 2, 3 until 15. Now the base is 16. We don't reach 16. The base is 16. Mistakenly, I said it earlier. Okay. So what do we have? The binary is represented by 4 digits. Okay, this is the idea here. 4 digits. Even 0 is represented by 0, 0, 0, 0. 4 digits. Alright. Hexadecimal goes from 0 until 9, same like decimal. Then we don't have 10. We don't go to two-column number. Rather we say A, B, C, D, E, F. F is represented by 1, 1, 1. That's 15 in decimal. Remember these combinations, they are critical. Don't memorize them, just have a look how they change. Like for example, F is 1, 1, 1, 1. 0 is 0, 0, 0, 0, all zeros. These are critical in, between decimal, binary and hexadecimal, okay? So explain about those now. As I said earlier, these are key numbers. F, 0, also FF. FF is extremely critical and used widely in between binary representation and hexadecimal memory, sometimes addressing and so on. FF is actually composed of 8 ones. 8 ones. So 1, 1, 1, 1. These are 4 ones for the first part, then 1, 1, 1, 1. Second part, that's FF. FF base 16 is 255 in decimal. And maybe it makes sense to you now. 255 is what? Try to remember. Okay. How about this one? We don't read it 100. It's not. 100 is for decimal. We read it 100, but base 16. Why? Because if you say 100, you mean it is base 10. These numbers that we have 10, 20, 30, they are base 10. But for 16, we say 100 base 16. Okay? Its representative, or the equivalent to it in digital, we said for each digit, it has its own 4 binary digits from hexadecimal. So 0 has 4 zeros here. The other 0 has 4 zeros. Okay. Then 1 remains on its own. Why? 1 is actually for all systems or counting systems is the same. 0 is also same. But for 1, we need to represent it by 4 digits. So it's a 0, 0, 0, 1. We don't have to write these zeros here. It's not necessary. Okay. And that's exactly the point. So we skip the zeros to the left and the number remains. What is this in decimal? That's 256, and that's also important, an important actually number in binary system. Okay. How can we convert between binary to hexadecimal or hexadecimal to binary? These conversions are really easy and convenient. We start by binary to hexadecimal. Now we have a binary number like this, or whatever the number is. We start from the least significant bit from here. Let me take the pen, let me get it. We start from this side, and then we group 4 bits each time. So we take 4. These 4 bits, we convert them to hexa. So we take another 4, another 4, another 4, and that's it. So let's take the first one. Let's start with the first one. 0, 1, 1, 1. How do I convert it? Take the weights. This is 8 plus 4 plus 1. So 8 plus 4, 12. Sorry, I'm sorry, 4. I said 8. This is 8. This is 4 plus 2 plus 1, 4 plus 2, 6 plus 1, 7. I said 8, it should be here. Actually, this one again, this is 2 to 0, 2 to 1, 2 to 2, 2 to 3. Okay, so 2 to 2, that's 4, plus 2 to 1, that's 2, 6, plus 2 to 0, that's 1. Okay, so this is 7, good. How about this? We have here 2 to 3 is not there, 0. 2 to 2, that's 4. This one there is no. 2 to 0. So 4 plus 1, 5. Okay, here, how about here? We have 8. Yeah, this one made me confused a bit. So 8, we don't have 4. We have 2, so 8 plus 2 plus 0. So we have 12. We don't say 12. We start by 10, which is A, then 11B, then C. Okay? Now here's the thing. We have 8 plus here, we don't have 4. What we have 2, 8 plus 2, that is 10. So what we count, 10 is A. Okay? Take the last one. We have 8 plus 4, that's 12. So we count 10, which is A, then 11B, 12C. So 12, this is 8 plus 4, 12, which is C. Okay? Let's take another example, if it is not clear enough to you. The second one, let's say here we start from the LSB, the least significant bit, and we group 4. The first 4, here we have 8. 8 means based on the weight. Now, how do I know this? The weight here, 2 plus 2 to the power of 3, which is 8. 2 to the power of 2, 2 to the power of 1, 2 to the power of 0. These are the weights. So this is 8, 2 to the power of 3, we have 1. Here we don't have any, They are zeros, so they cancel their weights. And here we have 1. That's 9. We put it the way it is with no problem. Okay? Take the next 4 bits. Here we don't have 8, we have 4 plus 2. 4 plus 2. Why? 8 is not there. Here we have 4, here we have 2, here we have 1. 1 there is no, 8 there is no, so 4 plus 2, that's 6. Okay? Then, how about this? Take this one. That's clear. We don't have 8, we don't have 4, we don't have 2, we have 1, so it is 1, the way it is. How about this? We have all the numbers. We have 8, 4, 2, 1, that is F. So 1, 1, 1, 1 is F directly, is 15. 8 plus 4, that's 12, plus 2, 14, plus 1 is 15. 15 is F. Okay, we have 2 only. How can we deal with them? Add zeros, like here. Zeros to the left, they change nothing. So we have here, what, 0, 0, 8 is not there, 4 is not there, we have 2 plus 1, that's 3. I hope it's clear. Start from the rightmost, move to the leftmost. If you have 1 or more digits here, just embed zeros, add zeros in front of them, and that will compose for you the hexadecimal last digit. Okay. How about hexadecimal to binary? The same way we applied here, we divide the digits into 4 and we compose a hexadecimal number or representation. There we take the hexadecimal digit and we compose 4 bits of it. Then we line them up, or we put them by each other, beside each other. So what happens? Let's just take a simple example here. Let's take 1 or 2 of those. Let's take A and C. Now 4 needs or requires, because this is base to 16, base 16, it requires 4 bits. So we go from least significant to most significant. We start by the least significant digit. We go to the most significant digit. For itself, 4 means what? There is no 8, there is 4, then there is no 2, there is no 1. So 0, 1, 0, 0. 8 is not there, 4 is there. This is okay. Then we don't have 2, we don't have 0. Alright, let's take A. A is represented by 10 in decimal. 10 is composed of 8 plus 2, so we need 8. Okay? We don't need 4, it's not there. We need 2, and we don't need 1. So 1, 0, 1, 0. Alright, let's take 0, 0 is simplest. All of them 4 zeros. Then the last digit, 1. 1 is represented by 0, 0, 0, 1. You don't have to write zeros here. If you write them, it's fine, but you don't have to do that. Okay? Alright, let's take the last one. Here, this one. We start by 2. So we have the weights 8, 4, 2, 1. What do? We have 2, so we don't have 8. Here. We don't have 8. We don't have 4. We have 2. And we don't have 1. Alright, so it is 0, 0, 1, 0. Right, 4, the same applies. We have only 4 in the weights. The weights are actually 8, then 4, then 2, then 1. 8 is what? 2 to 3. 4 is what? 2 to 2. 2 is what? 2 to 1. 2 to power 1, that means. When I say 2 to, I refer here 2 to power. So 2 to power 3, 2 to power 2, 2 to power 1, and 2 to power 0. We have these weights for these 4 digits. Alright, how about 4? So we have 4 only. We don't have 8. So we have 4, 0, 1. Then we don't have 2, 0. We don't have 1, 0. So 0, 1, 0, 0. Let's apply to 7. 7 is composed of what? Not 8, for sure it's less than 8. It is composed of 4 plus 2 plus 1. 8 is not there, 0. 4 plus 2 plus 1. 0, 1, 1, 1. Take 9. 9 is composed of 8 plus 1. We have 8, we have 1, 4 and 2 are not there, or they are zeros. 1, 0, 0, 1. And that's it. Right. Sometimes we may need to deal with hexadecimal in terms of decimal. So we convert, or we need to convert the hexadecimal to a decimal code. How do we do it? We have an easy way to do that. We go through binary first, meaning what? Meaning we convert the hexadecimal to binary, then we convert binary to decimal. So we have an intermediate process or phase of converting hexadecimal to binary, then binary to decimal. If it works for you, just go ahead and do it. Why it is easy for us to convert hexadecimal to binary, for just each digit here of this hexadecimal is converted to binary, and then we convert this binary to decimal. If it works for you, that's fine. Let's take one of these two as an example. C is composed of what? A, B, C. That is 12. 12 means what? 8 plus 4. So we have 1, 0, 1, sorry, 1, 1, 0, 0 in binary. And in that case, we need to do what? We can convert this one to decimal. It's not hard. Then this one can be converted also. You compose the whole binary and then you convert the whole binary. Why I just said C as an example, but if you have one C, then you have to take it the way it is fully. Let's take B as an example, not this one. Let's take B. Okay, look at B. If we convert it to binary, each of these digits is decomposed to 4 binary digits in the conversion. 5 is composed of 4 plus 1. So 0, 1, 0, 1. Here 8, here 4, 2, there is no, and there is 1. 4 plus 1, 5. 8 is composed of actually only 8, so 1, 0, 0, 0. Okay. A is 10 in decimal, which is 8 plus 2, so 8, 4 there is no, 2, 1 there is no, so 1, 0, 1, 0. Alright, so we have our own binary number, we can convert it. How do we convert it? Weights, based on the weights. How many weights do we have here? We have, how many digits? 2, 4, 3 times 4 actually, 12 digits. 12 digits from 2 to 0 to 2 to 11. 2 to 11 plus 2 to 9 plus 2 to 7 plus 2 to 2 plus 2 to 0. Sum them up. It's a big number, yes, but it's not really hard to achieve, especially for base 2. Base 2 is going like twice each time, so you can remember these numbers. It's not very hard. All right. We have an alternative way. We can directly represent base 16 or the hexadecimal by its own weights, and in that case we can reverse the process and create a decimal number. How do we do that? Now the weights of hexadecimal, 16 to power 0, then 16 to power 1, 16 to power 2, 16 to power 3, and move on. It's exactly the same like 2 to 0, 2 to 1, 2 to 2, and so on in binary, exactly like 10 to 0, 10 to 1, 10 to 2 in decimal. Alright, now let's apply the direct method. Let's take one of these two, just an explanation because I don't want to run mathematical calculation here and multiplication. 5, it's actually multiplied by 16 to 0 means 5 times 1. Anything to power 0 except 0, of course. 16 to 0 means 1. So 5 to 1. This is 5 to 1. Sorry, 5 multiplied by 1. Okay, 5 times 1. How about E? Here the base increases. E times 16. What is E? A, B, C, D, E, F. So that's 14. 14 times 16 plus 5 times 1. So it's just a matter of mathematical calculation, nothing else. If you want to do the same process to this, you can start from here. That's 11 times 16 to power 3, sorry, 0, 1, 2, 3, 4. 4, not 3. 16 to 4, then 2 times 16 to 3, then 15 times 16 to 2. No, mistakenly I said, sorry. This is 11 times 16 to power 3, 2 times 16 to power 2, 15 times 16 to power 1, 8 times 16 to power 0. Sum them up, and that's it. Okay. Well, a big number, yes. Usually we don't bring such calculation in the exam. It's just it's not wise. It needs mathematical calculation process, long one, which is not a matter of inspection of your knowledge now. We rather would go for maybe this one which is much more convenient. Okay. All right. How about decimal to hexadecimal? If we want to convert a decimal number to hexadecimal, in that case, what kind of method can we do? It's easy. We can use the repeated division by 16, the same way we applied the repeated division by 2 to go binary. What does it mean? Let's go to an example immediately, directly. This is a simple example. Let's say we are going to convert 650 in decimal to hexadecimal. We divide it by 16. There will be two parts of the composition, an integer part, this part, and a mantissa. What we need to do is we take the mantissa, multiply it by 16, it will produce some number. And of course this number will not be fraction, will not be mantissa, it will be integer. Because the division, the original division, is by 16. So if we multiply the mantissa by 16, it will not go integer, it will not go mantissa, it will go integer. Okay, this will be our LSD. Okay, the least significant digit. All right. Now, what are we going to do? We take the integer part and divide it by 16 again. So 40 here, the integer part. Don't ask me how did you do it. This is just a division. Okay, a division. If you are not quite sure, use the long division or whatever calculator if you are unable to use the long division. Okay. Divided by 16, you will have two parts. The integer part, leave it now. Take the mantissa, multiply it by 16, you get a number. This will be next to the LSD. So you move from right to left, not left to right. From right to left, from LSD to MSD. All right, take 2. You don't have to divide it actually. It's the remainder. You don't divide it. You don't have to divide it. Just place it directly here. If you want to divide it, you will get mantissa. If you multiply it by 16, you will get 2 again. So that's it. What you need to do is here, you just need to get this as a remainder because there is no integer here of this division. 2 is less than 16. It's represented by its own hexadecimal. Let's say we have 15 here also. You don't have to divide it because 15 is represented by F in hexadecimal. All right. So this will be our arrangement. LSD is the first one, first remainder that we have. Next to it, next to the LSD. Next to it is next to the LSD. We don't call this one MSB and LSB. These are not bits. These are digits because they are hexadecimal. Hexadecimal means another system or counting system which is not binary. For the binary digit, we call it a bit. Okay. Can we add hexadecimal? Yes, we can, but it has some rules, and these rules, we must apply them while adding. Now, basic rules is like this. If we are adding two digits, and these digits, the sum of them goes below 15 in decimal or F. Okay? What does it mean? Now, in hexadecimal, we have a count from 0 to 15, which is F, right? Yes. In that case, if the digits that we are summing up, their summation is less than F, well, we are still in the hexadecimal, then we have no problem. We can sum them up. But if they are above 15 in decimal or F in hexadecimal, then what we need to do is we need to subtract 16 from the outcome and then pass a 1 to the carry. Maybe it's not clear. Let's take an example. Let's just take two simple examples. One of them applies to the basic rules we just said now, when the digits, the composition or the addition of the digits will not reach to 15 or F in hexadecimal, and another way when it exceeds. Let's take A. Now look at A. 3 plus 6. Now sum them up in decimal. 3 in decimal and hexadecimal is same. Also 6 in decimal and hexadecimal are also same. So 3 to base 16 or 3 to base 10 are same. 3 plus 6 is 9 in both cases. It wouldn't change. Alright. 2 plus 1, same. What applies to 2, what applies to 3 applies to 2, what applies to 3 applies to 1. They are in both hexadecimal and decimal numbers. So 2 plus 1, 3, that's it. 3, 9. We don't call it 39. 39 is only for decimal. We call 3, 9 base to 16. Take another example now. 8 plus 2, that's less than F. That's less than 15. Okay, less than equal. So what we need here, 10. We don't call it 10 in decimal because we are summing up in decimal. So what we do is we say in hexadecimal it is A. 10 in decimal is A in hexadecimal. All right. 5 plus 2. 5 plus 2 is actually 7 in both hexadecimal and decimal. Let's take another example. When we have an extension, a number that passes F. Let's take D directly, the last example. F plus C. F converted to decimal, that's 15. C converted to decimal, that's 12. So 15 decimal plus 12 decimal, that's 27. 27 is not a valid digit in hexadecimal, so we need to get it back to the valid digit. We need to subtract 16. We need to subtract the base. So 27 minus 16, that's 11. 11 is a valid hexadecimal, which is B. Okay, so we have one carry. Why? Because we subtracted 16. We need to take 1 to the carry. Where? Here, to this part. Okay, D plus A in decimal. D is 13 plus A is 10. How do we know? A, B, C, D. So 10, 11, 12, 13, 14, 15 until F. Okay, do not forget that we have carry. We drop it down. Same like normal mathematics. Okay, so we have 23 plus 1, 24. 24 is not a valid, again, is not a valid hexadecimal. We need to subtract 16 from it. Do that. So 24 minus 16, that's 8. 8 is a valid hexadecimal with the carry 1. Do not forget, when you subtract 16, that means you are carrying 1 to the next column. Next column, we carried 1 from here to here. Then we need to carry 1 from here to the next column. Do we have? We will create. We don't have, we create it. The outcome, you start from here. We have 1 carried, then 8. This is 8. We got it here. And then we have B. So 1, 8, B. If you understand this, you can apply it to any example. Subtraction. Subtraction is a special type of addition. If we want to subtract hexadecimal, then we have to go to the 2's complement. 2's complement of hexadecimal numbers. You remember in binary what we did? We added the numbers after taking the 2's complement of the manuand, right? Sorry, the subtrahend. We have the manuand and the subtrahend. We took the 2's complement of the subtrahend, and that got us the negative value of the binary number. So we added a number with a negative value of another number. That is exactly subtraction. We can do this with hexadecimal. How to get the 2's complement? We have 3 methods. The first one is like this. Now look, I can show you in schematic diagram like this. We have the hexadecimal number. We convert it to binary. Take the 2's complement in binary. Okay, convert the binary to hexadecimal. Then we have the 2's complement of the hexadecimal. That's it. How? 2a converted to binary. How? For a we have 4 digits, for 2 we have 4 digits. A is 1010, this is 1010. 2 is 0010. Take the 2's complement. How do we take the 2's complement? Count from the rightmost until you catch the first one. Okay, we call the first one here. Keep them. Then take the 1's complement of the rest. So this one will be 1. This is 0, 1, 0, 1, 1. Therefore, we have 1, 1, 0, 1, 0, 1, 1, 0. Okay, convert this one back again to hexadecimal. How to convert it? Take 4 bits from the least significant to the most significant. This is 4 plus 2, that's 6. This one is 8 plus 4 plus 1, that is 13, which is D, D6. So 2a in hexadecimal as a positive and complemented number, its negative value, or the complement, 2's complement of it, is D6. You may say, how about the negative? There is no in this case. We don't have negative in binary system. We don't have negative in hexadecimal system. We have negative in decimal system because we human beings understand the the negative as a sign. But in computer, it's not understood this way. It's understood by 2's complement or 1's complement, and then we add, we sum up. Okay. We have another method. The other method is like this. Let me show directly from the schematic diagram. We have the hexadecimal. We subtract it from the maximum. Maximum means what? F. F is the maximum. Then we have the 1's complement in hexadecimal. We add 1 to it. Remember, 1's complement, if we add 1's complement of the binary, we add 1 to it, then we get 2's complement. It applies also to the hexadecimal. We subtract the maximum. We subtract this number, we subtract the maximum from this one, okay? Then what we get 1's complement, add 1 to it, we will get the 2's complement. Now 2a again, we will use FF, why these are 2 digits. FF minus 2a. How do I do this subtraction? Use the decimal representation of these numbers. So we have 15 and 15, 15 minus 10. That's 5. 15 minus 2, that's 13D. Add 1 to it, D6. So you got it. Okay. There is another method. What we need to do, look at the schematic here. We have hexadecimal. Instead of confusing us much, what we need to do, we need to list down all the 16 digits of the hexadecimal from 0 to F. So 0, 1, 2, 3 until 9, then A, B, C, D, E, F. Then we need to reverse the process. We need to list down F, E, D, C, B, A, 9, 8 until 0 opposite way. So F will meet 0, E will have same line, or actually lined up with 1, D with 2, C with 3, and so on. Then what? In order for us to get 1's complement, F is the 1's complement of 0, E is the 1 complement of 1, or 1 is the 1's complement of E in hexadecimal, and so on. So these two, like this, these are the 1's complement of each other. If we are thinking about 2a, okay, 2 is complemented, 1's complement of it in hexadecimal is D, and a 1's complement of it is is 5. Add 1 to it, we get 2's complement. 2a will be converted to 1's complement in hexadecimal to D5. Add 1 to it, D6. That's the 2's complement. Then sum the numbers. Let's take an example. Let's take just a simple example like this. 84 base 16 minus 2a base 16. How do we do it? Now, the easiest way is to take the 2's complement of the subtrahend and then sum up, add them, not subtract them. How to get? We explain 3 methods. Use whichever method you see is suitable for you. If you like to change to binary and take the 2's complement, that's up to you. If you want to subtract the maximum, okay, subtract the number from the maximum, that's up to you. If you want to use this method, also up to you. It's totally up to you. Choose whichever method you like in the application. All right, so here what are we going to do is something like this. Now we have 2a, we can convert it to binary. Take this method, so we can convert it to binary. A is converted to 1010, and then to 0010, okay? 2's complement, we said we move until we catch the first one from rightmost to leftmost. So we call the first one here. Then we convert those, or we take the 1's complement of those. This one will be 1 0 1 0 1 1. So the number again will be 1 1 0 1 0 1 1 0. This one. Okay, that is the 2's complement, which is the negative version of 2a in hexadecimal. Sum them up means what? Place 8 4 plus, no more minus, because we took the 2's complement, which is supposed to be negative in this case. 4 plus 6, that is a in hexadecimal. 8 plus d, now remember the rule, now 8 plus d will go beyond 16, beyond 15, and for that case we need to subtract 16 from it and then take a carry. Apply what we explained earlier, so you will have 5, and then you will have 1 in the carry. Ignore it. This carry, remove it. Why? This is a subtraction, not addition. If it was a real addition, yes, you would just need to keep this one. This is not a real addition. Apply the rule of addition, yes, but ignore the carry. Okay? Take another example if this one is not quite clear. Now what we need to do is, initially we need to convert the subtrand to 2's complement. Now this is the subtrand. 0b. 0 is all zeros, 4 zeros. B is represented by 11. So 11 is 8 plus 2 plus 1. So 8, that's 1. 0, 1, 1. Okay. Then we got this 2's complement converted back again to hexadecimal. Hexadecimal, this is all zeros, so that's 0. We need to get the 2's complement of this. How to get the 2's complement of this? Hold the first one we get from right side, then take 1's complement of the rest. So 1 1 1 1 0 1 0 1. This is the number. This is the 2's complement. This 2's complement is represented by f. This is f. 1 1 1 1 is f. Then we have 4 plus 1, that's 5. 0 1 0 1, that's 5. Okay. F5 and 16, we need to add C3 to F5. 3 plus 5 and 16, base 16 is fine, is 8. There is no problem. But C plus F is beyond 15, which means we need to subtract 16 from whatever the result here, and we get the decimal number of it. Then we ignore the carry. The same rules we applied earlier. Okay. The octal number system, we have also another numbering system. We call it octal. It's base of 8. Its base is 8. We have here, in this case, we have 8 digits from 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. You may say, why do we need to do it? Why do we need to use it? It has a lot of applications, and remember that it is exactly half of the base 16. So it makes some sense, and we will see why and how. All right. Okay, so after 7, we don't count 8. There is no 8. We go to 1 0, and we don't call it 10. It's not 10 now. It's not decimal. It's 1 0 base 8. Or you can call it base O, octal, or Q also. One of these three. Either base 8 or base O or base Q. It's up to you. All right. Can we convert between octal to decimal? Sure, we can do that. There is no problem. We can use the weights, and these weights, you can multiply each number by its own positional weight to get the total value to decimal again. If you think about this number, 2374 in octal base or 8 base, if we want to convert it, remember this one to base 8 to 0 multiplied by 8 to 0 multiplied by 1. This is multiplied by 8 to 1, means multiplied by 8. This is multiplied by 8 to power 2. This is multiplied by 8 to power 3. Sum them up, you will get the value. It's just base of mathematical operation, nothing else. There is no much of calculations here. How about decimal to octal? We can use the long division by 8, so repeated division by 8. We apply the repeated division by 2 for digital or binary. We apply the repeated division by 16 for hexadecimal. We apply the repeated division for 8 to 8, the same procedure. So what do we need to do? We take a number which we want to convert it to base 8. We divide it by 8. We will have two parts, the integer part and the remainder, or the mantissa in this case. Take the remainder or the mantissa, multiply it by 8 again, so that you will get an integer number. This is the LSD again, LSD, okay? And from this LSD, what you need to do, you need to move on to the next using the integer part. Take the integer part, divide it by 8 again. You will have an integer part, suspend it, leave it for a while now. Take the mantissa or the fractional part, multiply it by 8. You will have the next digit from the LSD side. Then take whatever remainder here. If it is less than 8, you don't have to divide it. It's not necessary, it's a remainder by itself. So if you divide it and multiply it by 8, it will get you to the same 0.5. That's the final number, or the MSD. So it's organized this way: 5, 4, 7 MSD from this side. 5, 4, 7. All right, that's the way. I don't need to repeat it because already explained. How about binary to octal? Binary to octal is extremely simple and straightforward. What we do, we convert each digit from octal to binary in 3 digits. Now hexadecimal in 4 digits. For octal, no, only 3 digits will do. And that is one of the reasons we use the base 8. Very similar to the hexadecimal. Each digit from the hexadecimal is converted to 4 binary digits. Now each digit from the octal is converted to 3 binary digits. And that's one of the, you can say, attractive features that we have in octal system. All right. Let's check. For 0 we have 0, 0, 0, and binary 1, 0, 0, 1, 2, 0, 1, 0, 3, 0, 1, 1, 4, 1, 0, 0, 5, 1, 0, 1, and 2, 7. Actually, let's go through them, all of them. 6, 1, 1, 0, and 7, 1, 1, 1. That's it. They are extremely convenient. So how do we do it? Well, you have the digits and you have the conversion. Just stick them together. How about if I have, like, let's say 6, 7 in octal? That's fine. You can start each one by itself as a block. 6 is converted to 110. 7 is converted to 111. Oh, well, that's very convenient. Let's take an example. Let's take this one. Let's take this. 0 is converted to 0, 0, 0. 4 is converted to 1, 0, 0. 3, we said. So 1, 0, 0. And 1 is converted to 0, 0, 1. If you cancel those, also fine, no problem. Because in this side, usually we don't consider zeros. But if you keep them, that's also fine. Take any other. Well, take this one. 7 is 1, 1, 1. You want to start from this side, that's fine. You want to start from this side, is also fine. There is no problem because they are separate digits in this case. Okay? 1, 1, 1. 5 is 1, 0, 1. 2 is 0, 1, 0. 6 is 1, 1, 0. That's it. Okay, binary to octal. How about the other way around? We start from the rightmost, like what we did in hexadecimal. We group the bits of the binary to 3 blocks of 3, not 4. Now we speak about octal. If we are left with a 1 or more digit less than 3, so 1 or 2, then we add 0. We add zeros and we have what we call like the leftover representation in this case. How? Let's see. We'll take a few examples. Now group those in a block. Group those in a block. These are two blocks of 3, 3, so we have no problem in here. We have, this is 4 plus 1, that's 5. Here we have 4 plus 2, that's 6, so 65. Okay, take this one, 3, 3, again 3, so we have no problem here, it's fine. You can start from the rightmost always, you should start from the rightmost. Why? Because we may be left with only 1 or 2 digits, so we can add zeros. But here in this case, it's equally divided to 3. What does it mean? Now, this one is represented by 1. 1 in all numeric system is 1. 0, 0, 1 is 1, so this is 1. This is 7, and this one is 4 plus 1, that's 5. So here we have 5, 7, 1 in octal. Let's take another example. Let's take this one. Any of them has no equal division. 3, 3, 3. Yes, 2. This is good. Is it? Yes. So we take 3, then 3, then 3, then 2. So what we do here, we add 0. Okay, we add 0 at the end. All right. Here 1, 0, 0, that's 4. 0, 0, 0 is 0, 0, 1, 0, that's 2, and then we have 0, 1, 1, that is 3. So here we have, sorry, I said 2, then here 3. Again, this one is 4, 0, then 2, then 3. Okay, 3, 2, 0, 0, 4. That is how we read it. We don't read it like 3204. No, this is base 8. 3204. All right. Binary coded decimal, this is a very common code that we usually use in computation. Why do we use it? I will explain in a while, but it is a code we call binary coded decimal, or BCD, or sometimes we name it 8421 based on the weights that we have. Any value is composed from the weights 8, 4, 2, 1. If you sum them up, 8 plus 4, that is 12 plus 2, 14 plus 1, 15. These are the weights that we have here. So 15, well, 15, how many combinations do we have? We are actually interested in only decimal digits. Decimal digits go from 0 to 9. That means we have only 10 digits. But I said I can compose 15 based on these weights. Yes, but we are interested from 0 to 9. So we ignore. If you want to call it 10, 11, 12, 13, 14, 15, we ignore them. Or if you want to call them A, B, C, D, E, F, also we ignore them. We ignore those. We are interested only in digits from 0 to 9. Why? These are the decimal digits, and we are interested in exactly coding decimal digits. We are not interested in coding A, B, C, D, or 10, 11, 12, 13, because they are not valid decimal digits. All right. So look at the decimal digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the representation in BCD. BCD represents each of these in 4 digits. Now, you may say, fine, no problem. Why do we say we have 8, 4, 2, 1? Because if we want to represent each decimal digit by 4 digits, then we must go through those. Why? They compose for you the possibilities from 0, 0, 0, 0, to 1, 1, 1, 1 in total, but we are not interested in 1 until 1, 1, 1, 1. No, we are interested until 9, which is 1, 0, 1, 1. The rest of the codes are invalid. We have other codes other than 9. We have 10, 11, 12, 13, 14, 15. They are invalid. We don't use them. They are called invalid. So here 10 is invalid. 11 is invalid, 12 is invalid, 13 is invalid, 14 is invalid, 15 is invalid. These are all invalid codes in BCD. BCD specifically. We speak about this system. Okay. All right. So this is BCD. How do we convert a decimal number to BCD? Take each digit apart, convert it to 4 binary digits. Each decimal digit, like 5, it must be converted to 4 binary digits. So 5 is composed of 4 plus 1, that is 0, 1, 0, 1. How about 3? 3 is 2 plus 1, 0, 0, 1, 1. I hope you guys catch what I say, 2 plus 1. 2 plus 1, that means the positional weight here, the positional weight here. The positional weight, 8, 4, 2, 1. I hope you catch it. And 3, for example, is composed of 2 plus 1. So positional weight here, 1, place 1, 1, so those are zeros. Take another example, maybe that will make you understand it in a better way. Now look at this, 9, 8, 9, we have 9 here as a value is composed of what? Is composed of 8 plus 1. The positional weight of 8 plus the positional weight of 1. The others here in the middle are zeros. How about 8? The positional weight of 8, you place 1, the rest are zeros. And you go on with that, same like any other, take any other representation, 9 again, 8 plus 1, so that is 1, 0, 0, 1, and you move on. Each of these digits is distributed over 4 digits, or actually converted to 4 digits of binary. All right. How about getting or converting the binary coded decimal to decimal? So if we have it in binary, how can we convert it? Again, we start from the rightmost, we group 4 bits each, then we convert it. How about if we don't have 4 bits here, you add zeros to it, so there will be no problem. Now look at this, we have the positional weight of 8 is not available, we have the positional weight of 4, so we have 4 plus 2, that's 6. How about here, we have the positional weight of 8, no 4, no 2, no 1, okay? So here, 8. Take any other example, take this one, 4, this is 0, because all zeros, take another 4, 4 plus 2 plus 1, 7. Take another 4. We have 0, so we don't have 8. 4 plus nothing, so that's 4. So here, 8 is not there, only 4 is there. No 2, no 1. Okay, how about this one? We have 8. We have 1, 8 plus 1, that's 9. That's it. All right. Can we add BCD? Yes, it's a code, it's a decimal code a binary code that can be added. Why? Because we are coding decimal numbers to binary. So we can apply all arithmetic operations, we can add them, multiply them, subtract them, divide them, and so on. But what is the most critical in computation in terms of operation is the actually arithmetic operations is the addition. Why? If you think about subtraction, it's composed of addition. Why? We take the 2's complement of a number, then we add them. Multiplication, we have shift and add, so it goes ultimately to adding. Division also, we have also some type of shifting and adding, but in complement way, or 2's complement way. Right, how about the addition? The addition, we have basic steps for the addition. What we need to do now, we can add the 4-bit, sum the 4-bit. Each digit has its own 4-bit in binary, right? We can sum them up. If they are less than or equal 9, so less than or equal 9, then there is no problem. We are in the safe side. This is a valid BCD. There is no problem with that addition. But if it is greater than 9, then it is an invalid BCD. And what we need to do is we need to move it to a valid BCD. In order for us to move it to a valid BCD, we need to rotate it, like circle it. Circle it or cycle it can be done by adding 6. Why? Actually, we have 10, 11, 12, 13, 14, 15, these are 6. If we add 6 to the number, it will rotate back again to the beginning, whatever it is, an invalid BCD code, it takes you from invalid to a valid BCD code. But in that case, we will have a carry. Take the carry to the next column, and then that's it. That is what you need to do. The carry will be just taken to the next column. All right. Let's take an example. Maybe it is a bit vague. Let's take two simple examples. One of them applies directly with no carry, with nothing. The other one needs some special manipulation. Let's take this one. 0011 plus 0100. For 0011, that's 3, we know it. 0100, that's 4. Okay, so 3 plus 4. 1 plus 0, that's 1. 1 plus 0, that's 1. 0 plus 1, that's 1. 0 plus 0, that's 0. Is this a valid BCD? Yes, it is 7. 0, 1, 1, 1, that's 7. That means 4 plus 2 plus 1. Okay, that's good. Let's take another example, D. Now think about it. This is also a simple example. Let's line them up. So this one on top of this one, take 4, 4 each time. 4, 4, divide them to 4, 4. If the last one is not 4, add zeros to it. Okay, 0 plus anything is the same thing. So this is a valid, again 7. How about this one? 1 plus 1 is 0 with 1 carried. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0, 0. That is 4 plus 2, 6. There is no problem. Here, how about this one? 0 plus 0, 0, 0 plus 0, 0. 1 plus 1 is 0 with 1 carried. 1 plus 0 is 1. That's 8, and it's also fine. Let's take another example. Okay, let's take this one. 1, 0, 0. 1 plus 0, 1, 0, 0. Now 9 plus 4 is more than 9, and that creates a problem. Let's see how we deal with it. 1 plus 0, that's 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. So 1, 1, 0, 1. This is an invalid BCD code. We don't have a BCD code like this. We need to add to it 0, 1, 1, 0. That's 6 in decimal. Add it to it. 1 plus 0, that's 1. 0 plus 1, that's 1. 1 plus 1 is 0 with 1 carried. 1 plus 1 is 0 with 1 carried, plus 0 is 0. So we have 1 somewhere carried. Keep it aside. This one is a valid BCD, and we have a carry. So it is no longer just 4 or 1 digit of BCD, 4 bits. No, it will become 8. We have a carry. Carry of 1 will be 001. It will be carried to the next level. The same applies. If you check, let's leave B, let's take this one. This is a bit harder, C. We have 0, 1, 1, 0 plus 0, 1, 0, 1. Okay, 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0 with 1 carried. The 1 carried will be represented in this digit, the last one here. Okay, now here's the problem. This one is 8 plus 2 plus 1, which is greater than 9. Okay? It's invalid in BCD. We need to add 6 to it. 6 is represented in digital 0, 1, 1, 0. Okay? Add 1 plus 0, that's 1. 1 plus 1 is 0 with 1 carried. 1 plus 0 is 1, plus 1 is 0 with 1 carried. 1 plus 1 is 0 with 1 carried, plus 0 is 0, so we have 1 carried here. 1 taken to this side. Alright, so we have 1 taken to this side, we add it. 1 plus 1 is 0 with 1 carried, plus 1 is 1. Okay, so, and we have 1 in carry. Or, if you want, you can add these two at the beginning. 1 plus 1 is 1, 0. Then you add the carried 1 to it. We have 1 in carry here, right? From previous operation here, this one. Or if you want, you can add it to this side directly. 1 plus 1 plus 1, that's 1, 1. 1 plus 1 is 0 with 1 carried, plus 1 is 1. And we have 1 in the carry, it will be 1, 1. So we have 0, 0, 1, 1. I hope it's clear. Okay, let's take the last example so that if it is not clear, you will understand it. If we speak about this kind of BCD, we have these 2 digits from BCD, 2 digits, that means they're presented by 4 binary bits each. Sorry, 8 binary bits here, 2 digits. 2 digits means this one is what? This one 6, and this one is 7. So 6, 7 in BCD, and here we have 5 and 3. This is what I said, 2 digit. 6, 7, 5, 3. Alright, now look at this. If we add 1 plus 1 is 0 with 1 carried, 1 plus 1 plus 1 is 1 with 1 carried, 1 plus 1 is 0 with 1 carried. So here 1 plus 0 we have 1. 1, 0, 1, 0, that's 10, and that case is greater than 9, and it's invalid. We need to add 6 to it. 0, 0, 0, sorry, 0, 1, 1, 0, that's 6. Add it. 0 plus 0 is 0. 1 plus 1 is 0 with 1 carried, again 0 with 1 carried, again 0 with 1 carried. So we have 1 somewhere carried here. Okay, let's do this operation first. Okay, 0 plus 1, that is 1. 1 plus 0, that's 1. 1 plus 1 is 0 with 1 carried. So we have also here invalid operation. Okay, so for this invalid operation, what do we need to do? We need to add 6. So, invalid, not operation, invalid code. It's invalid BCD code. Add to it 6. 1. Why invalid? It's greater than 9. Okay, 1 plus 0, that's 1 plus 1 from before. We have 1 from here. So we had this one, right? We had 1 from a previous operation here. Okay, add 1 to it, it will be 0. Then again 1 plus 1 plus 1 is 1. Again 1 plus 1, sorry, 1 plus 0 plus 1 is 0. 1 plus 1 is 0 with 1 carry, then we have a carry to the next level. Remember that we had a carry from here. That's why it must be added to this operation. All right. I hope it's clear. This is the end of the third part of this chapter. We will have a final part. Until then, have a good time. Goodbye.